Greetings, welcome to our 45th episode of the FGI podcast series. My name is Tim Stark and I'm a professor of civil engineering at the University of Illinois at Urbana-Champaign. On today's episode, we are going to focus on our November 10th, 2022 webinar titled Strengths and Uncertainties Regarding PFAS Containment by Modern Liner Systems. I'd like to quickly reintroduce our distinguished presenter, Dr. Kerry Rowe. He's a distinguished university professor and Canada Research Chair in Geotechnical and Geoenvironmental Engineering at Queen's University in Kingston, Ontario, Canada. Kerry's been involved in geosynthetics for many years, published over 440 peer-reviewed journal articles and 350 full conference papers. So, Kerry, thank you so much for joining us again and presenting a great webinar.
You're welcome.
Great. So we have some questions remaining from the live webinar, and then we have some questions submitted after the webinar. So the questions from the live webinar. Number one, what was the composition and concentration of the PFAS in the HDPE geomembrane testing?
Well, it so happens that since the webinar, a paper has been published by Rowe and Summa in the Journal of Environmental Management, volume 328, and all of the details are given there, but very briefly I will answer the question. We studied the geomembrane in three different solutions. One was a synthetic municipal solid waste leachate. The second was DI water with about 28 milligrams per litre of calcium carbonate added to make it less aggressive, because DI water can be quite aggressive. And we added to that PFAS. And the third solution was PFAS added to the synthetic municipal solid waste leachate. And I reported results for those three cases. And the most aggressive was the PFAS plus synthetic municipal solid waste leachate. But the PFAS and DI water, a little calcium carbonate, was more aggressive than just synthetic municipal solid waste leachate. So the PFAS did have an effect. And the next part of the question was, what were they and how much? And we had about 20 milligrams per litre of three different PFAS. The first was perfluoropentoic acid, or PFPEA. The second was perfluorohexanoic acid, PFHXA. The third was perfluorooctanoic acid, or PFOA, and the last was perfluorooctane sulfonic acid, or PFOS. Those concentrations at 20 milligrams per litre are quite high, but the first study was to see, did it have a notable effect? When I say they're quite high, they're still very small compared to the amount of surfactant that was already in the synthetic municipal solid waste leachate. So we're comparing 20 milligrams per litre with about 5,000 milligrams per litre for the other surfactants. So overall, it's a small contribution that had a big effect. We are currently doing studies with more geomembranes, including HDPE from different suppliers, various other geomembranes as well. And we're also looking at the effect of the concentration, and we're looking at concentrations of 1 milligram per litre as well as 0.2 milligrams per litre, in addition to the 20 milligrams per litre.
Great, Kerry. You mentioned a new technical paper. If it's available, it would be great if we could put it on the website with your webinar as well.
Sure.
Great. Okay, thank you. Question number two. How do you assess which geomembrane specifications should be used for an MSW landfill site? Problem is, what leachate do you test against, as what is disposed with time may change with time in the particular landfill?
Well, you're quite right that the leachate does change with time. We modeled our leachate on a relatively young leachate from the Kill Valley landfill. And it's a fairly strong leachate. It has a notable proportion of total dissolved solids, mostly salts. The predominant salt is sodium chloride. We have pH control and surfactant that are added to it. We did a study and published 2 papers, one of them in 2008 and a follow-up paper in 2014, where we looked at the effect of the chemical composition on the performance, initially on antioxidant depletion and subsequently on long-term performance. And we found that the key components were the surfactant, the total dissolved solids content, and the pH. And as long as you get those in roughly the right ballpark, that's the critical thing. And we found that the leachate that we use is a good surrogate for many leachates. It's stronger than many, but nevertheless, if it does well in our leachate, it'll do well in most municipal solid waste landfills.
Great. And Gary, you just mentioned the 2008-2014 paper. Again, would be great if we could post those as well.
Sure.
Okay, thank you. Number 3, in the UK, we use tire bales / shredded tires as a leachate collection layer. Is there a potential impact from tires? Is there any research that you are aware of that would suggest that there may be a PFAS impact from tires, and it would be prudent to cease using tires for this purpose?
Interesting question. We did some work a number of years ago, probably more than a decade ago now, on the use of tires in leachate collection systems. And there is some cautions that you need to take in doing so. But the question is more specifically on PFAS. And I haven't found any information about the PFAS that may be related to tires. A couple of years ago, the EPA and the CDC did a podcast on recycled tire crumb rubber. And at that time, at least, they indicated that they did not analyze for PFAS. So I don't know the question has been answered, certainly not to my knowledge.
Okay, great, thank you. Number 4, have you seen any PFAS concentrations in landfill gas and/or gas condensate?
Again, it's not something that I've looked at, but it's a good question.
Yep.
And in 2019, there was an article that looked at leachates from ash, construction, demolition landfills, and municipal solid waste landfills, as well as gas condensates from landfills. They looked at 26 PFAS species, and they found, very interestingly, high levels in the gas condensate. It had an average value of about 11,500 nanograms per litre and a maximum of 81,000 nanograms per litre. So these were certainly high compared to ash landfills, which had leachate at about 7,500 on average, although a peak value of 54,000 nanograms per litre, yet still less than the gas condensate. Construction and demolition landfills had an average of about 10,000 nanograms per litre, and municipal landfills had an average of about 19,000 nanograms per litre, but with concentrations up to 300,000 nanograms per litre. The predominant one being PFOA, which is about 215,000 nanograms per litre, or about 0.2 milligrams per litre.
Okay, great. Last question from the live webinar, number 5. After initial diffusion, wouldn't the rate slow because the concentration is increased below the geomembrane, thus the gradient is reduced across the geomembrane?
If the concentration did in fact increase below the geomembrane, then diffusion would be slow. But in fact, that's not likely to happen because the geomembrane will be usually sitting on either a GCL or compacted clay. And the diffusion coefficient through either of those is about 5 orders of magnitude higher than it is through the geomembrane. And so consequently, it will be diffusing away very quickly once it gets through the geomembrane and will not be building up there. So it won't slow the rate through the geomembrane. That rate, however, is very slow.
Okay, great. Gary, we have 4 questions that we received after your live webinar. So here's the first one. Regarding the OIT reduction in the presence of PFAS, what is the mechanism? Is it antioxidant leach out or antioxidant consumption with PFAS?
We think it's predominantly leach out because the antioxidants are diffusing out of the geomembrane, and the PFAS, we think, improves the wettability of the surface. A lot of those antioxidants are hydrophobic, and the fact that they have a surfactant out there, and more surfactant with the PFAS, appears to accommodate the faster leaching.
Okay. Next question after the webinar. Did you also look into PFAS, PFOA, diffusion coefficients through compacted clay liners? If the diffusion coefficients through geomembranes, especially HDPE, are low, should we be concerned about diffusion through GCLs, because most composite liners have a GCL or compacted clay, as you just mentioned, under the geomembrane?
Yes, we've looked at diffusion through GCLs, not through compacted clay, but we wouldn't expect it to be terribly different. Generally, the diffusion coefficient is lower through a GCL than it is in compacted clay, but they're of the same order of magnitude. And when we look at contaminants like chloride, we found more or less a factor of 2 difference, about a factor of 2 lower in the GCL than compacted clay. The diffusion, however, is, as I mentioned before, orders of magnitude higher through either GCL or suspected through compacted clay than it is through the geomembrane. So they're not acting as a terribly good diffusion barrier. If you want a bit of information, we will be publishing a paper, hopefully in the relatively near future, with those results. But one could conservatively, we've found, use the diffusion coefficient for chloride, and that's well published. There's a whole table of summarizing values in my barrier systems for waste disposal facilities book that was published in 2004.
Okay, great. Next question starts off, thank you for your wonderful presentation, Dr. Rowe. I agree. Great job, Carrie. Since the parameters, diffusion coefficient and hydraulic conductivity, are measured in saturated condition and an attenuation layer may be included, how can we evaluate the unsaturated clay barriers, GCL or compacted soil, in a composite liner system, which may be vulnerable in the field?
So that's quite a complex question, so I'll take a fairly long answer. Just starting with the simplest, which is GCL and compacted clays. They're usually at a degree of saturation that's high enough that it is conservative and reasonable to use the saturated values. Likewise, for an attenuation layer, if it is close to the water table, the attenuation layers that I talked about must, by definition, have a hydraulic conductivity of 10 to the minus 7 meters per second or less. And so they're fairly silty material, and that material tends to maintain a fairly high degree of saturation if it's near a water table. For soils that are higher hydraulic conductivity, or if you've got a very low water table, then you certainly get into the realm of unsaturated soil mechanics. Once we get into that realm, we've got to ask ourselves, is the transport in the dissolve phase, or the aqueous phase, or is it in a gaseous phase? If the transport is in the dissolve phase, then we know that the hydraulic conductivity of unsaturated soils actually decreases, and so they will act as a barrier to some extent and is beneficial. But if they go into the gaseous phase, the opposite is true. If you have a low degree of saturation, then gases can migrate fairly readily if they've got continuous gas-filled pores. And gas diffusion can be 4 to 5 orders of magnitude higher than diffusion through water. So depending on the nature of the PFAS, if they're in a dissolve phase or whether they're in a gaseous phase, you can get quite different results. Again, in our barriers book, the Barrier Systems for Waste Disposal Facility, we talk about how you model both the dissolve phase and the gaseous phase. With respect to PFAS, the volatilization of PFAS depends on the carbon chain length and its ionization status. They will tend to be in the air, water, or non-aqueous phase water interface area. That's where they preferentially go. If they get into an ionic form, they'll tend to be predominantly in the dissolve phase, but they can also transition to a non-ionic form, particularly in contact with organic solvents or organic matrices. And so depending on the environment, examples where they could easily get into a volatile form is in the presence of residues left from firefighting foams, fuels, bitumen. Those sort of materials could predominantly move them into the gaseous form or the volatile form. So you need to think about what's there with the PFAS in trying to answer that question.
Okay, great. Last question from the survey after your webinar. The attenuation layer in the Ontario regulations is much thicker than the clay/soil component of a composite liner system required by the US EPA. The specifications for the soil/clay component have a maximum saturated hydraulic conductivity of 1 × 10⁻⁷ centimeters per second. What are the hydraulic conductivity specs for Ontario's attenuation layer, and which is the more effective factor in limiting advection of PFAS contaminants, thickness or hydraulic conductivity?
Okay, so a number of issues here. Firstly, with compacted clay in Ontario, we expect a similar maximum hydraulic conductivity to the US, so a maximum of 1 × 10⁻⁷ centimeters per second, or as it's specified here, a maximum of 1 × 10⁻⁹ meters per second. And when you have hydraulic conductivities of that magnitude or smaller, the advective transport will be controlled by the hydraulic conductivity primarily. Thickness does play a role, of course, in affecting the gradient, but the hydraulic conductivity tends to be the more critical component when we have a GCL or compacted clay liner. When we get to the attenuation layer, as I said a few moments ago, in Ontario, by definition, to be an attenuation layer, it must have a hydraulic conductivity less than 1 × 10⁻⁵ centimeters per second, or 1 × 10⁻⁷ meters per second. And at that, it provides very little hydraulic resistance compared to the GCL or compacted clay. It's not there because of its hydraulic resistance, it's there because it is a good diffusive barrier. And so that is the reason that Ontario has the attenuation layer. And I should point out that Ontario's regulations weren't arbitrarily set. They were set based on modelling and ensuring that Ontario's allowable impacts were met for the particular landfills. When we've got a composite liner, a geomembrane and GCL, it's going to be the geomembrane that limits both advection and diffusion with the exception of holes. And work that we've done, and it's a paper I think was put up with the original podcast, has shown that with the typical leakage you get with a single composite liner, there are potential problems with PFAS escape that weren't recognized when current regulations were written. And certainly I would recommend in future double composite liners for anything containing a significant concentration of PFAS.
Carrie, on that recommendation of double composite, should there also be a leak detection zone between the two?
Oh yes, it should have a leak location between the double composite.
Great. Great, Carrie, thank you so much. That's all the questions from the webinar and the survey. So thank you again for joining us from Kingston, Ontario, and giving an excellent presentation on a real important topic, PFAS containment.
My pleasure, Tim.
And if you still have questions or would like additional information, you can send your questions to the FGI at fabricatedgeomembrane@gmail.com or download the webinar slides. And Gary, if it's okay, your email address is on the last slide. You can send your questions directly to Professor Rowe, and I'm sure he'll respond as soon as he can. So Carrie, again, thank you so much for joining us.
Good to be with you, Tim.
Thank you.